Proof assistants are insane. Errors that might take months to find can be done in minutes. Math problems become open source projects as anyone can contribute verified math code. AIs now have an environment to learn and generate verified math proofs. This video is the ultimate tutorial on the Lean 4 proof assistant. By the end, we'll be able to formalize these three big proofs using the law of the excluded middle, a proof by contradiction, and the axiom of choice. Don't worry, I'll be explaining the proofs in detail before formalizing them. The code in this video is given in the online Lean 4 web server linked below in the description, so you can follow along if you wish to. Let's start with syntax. Theorem TH is a proof of 2 equal 2, and its value is sorry. Anytime you see some H colon a proposition, it means H is its proof. Writing theorem before and assigning the proof after stores it in H. So what's the sorry doing there? It doesn't look like a proof. Well, where's the proof? I don't have it. Sorry. Fine, I'll let you off with a warning. Assumptions can be put before the colon, like H is a proof of 2 equal 2. So think about it. If H is the proof of 2 equal 2, then what is the proof of 2 equal 2? Obviously H. And the proof is accepted. What's going on here? Look at these two functions in C and Lean. Both are named ident, and they take in an integer n and output an integer, which is n itself. Taking just the Lean code, doesn't it look similar to theorem TH? When ident is given an integer 5, it gives back the same integer 5, making its type int to int. I can check ident to see this in the info view. Similarly, when th is given a proof of 2 equal 2, it gives back the same proof, making its type 2 equal 2 to 2 equal 2. Check th to see this in the info view as well. Since int is a type with 5 as a term, 2 equal 2 is also a type with its proof as a term. And that's the big idea. Propositions are types, and their proofs are their terms. Even false propositions are types, but they're empty since they have no proof. The phrase is a proof of and is of type mean the same thing when propositions are concerned. In ident, if I output a string value unkyog, the type checker clearly explains the error. Type mismatch, expected int but got string. In th, if I assume k to be the proof for 3 equal 3 and output k, look at the error message. It's the same. Type mismatch, expected 2 equal 2 but got 3 equal 3. The type checker that verifies ident's type also verifies th's type. There are two aspects of Lean we can use to help us with proving. The first is tactic mode. Instead of painstakingly writing every detail of the proof, tactics allow us to give broad instructions on how to construct the proof. Enter tactic mode by writing by after the theorem. Notice the tactic state pop up in the info view that tells us our assumptions and the goal. The first tactic we'll use is exact. Writing exact H closes the goal since it is exactly H. To prove 2 equal 2 directly without any assumptions, we can use the tactic norm_num. It normalizes numerical expressions and solves them. The second is Mathlib, Lean's math library. Imagine trying to prove theorem plus com for all a plus b equal b plus a. We don't write the complete proof for commutativity every time we need to use it. We know that someone has already proved it. Just go find it. In Lean, it's called nat.addCom, and it tells us that if you give it a nat a and a nat b, it will give us the proof that a plus b equal b plus a. Giving it 1 and 2 makes it a proof of 1 plus 2 equal 2 plus 1. But I cannot give this example as a proof. We must assume that a and b are arbitrary natural numbers, and then apply commutativity on them. That's the correct proof. How do we do this in Lean? Just write intro A, B. Look at the tactic state. We have two numbers, A and B, in our hypothesis now, and the goal has changed too. Let's have H be the result of nat.addCom applied on A and B. The have tactic allows us to have extra hypothesis. We now have a proof H of A plus B equal B plus A. And that's exactly what the goal is. Exact H. The proof is done. Notice that if I change the order of A and B, H is no longer exactly the goal, as the equality is flipped. Moving on, what if we wanted to prove that for all A, B, C, A times B plus C equals A times C plus B? We can start off similarly with intro A, B, C to assume arbitrary A, B, and C. If we could rewrite the first B plus C as C plus B, both sides would be equal. Let's have H be the proof that B plus C equals C plus B. Notice the new sub-goal in the tactic state. Quite similar to the last proof. Have G be nat.addCom applied on B and C. The sub-goal is now exact G. H is now in our list of assumptions. To rewrite H into the goal, I will use the tactic rewrite H, and B plus C gets rewritten as C plus B. Given any equality, the rewrite tactic will replace the LHS with the RHS. The goal is trivial now, and the rewrite tactic automatically solves it for us. Great, let's now solve this monster. No? Okay, that's why we have the ring tactic. Simply intro the variables and write ring. It'll solve most algebraic equations automatically. Despite how vast the world of proofs may seem, there are a few patterns we can notice when dealing with the laws of logic. On one hand, to prove a for-all statement, in this case plus com, we had to introduce the variables first and then prove the proposition. This is the introduction rule of a for-all statement. While on the other hand, using the given for-all proof, in this case using nat.addCom, involved giving it some input m and getting the proof of Pm in H. This is the elimination rule of a for-all statement. When you're formalizing proofs in Lean, you're translating logical arguments into the language of functional programming. If you want to build a solid foundation in logic and programming, a great place to start is Brilliant, the sponsor of today's video. What I love about Brilliant's approach is it makes it easy to learn anywhere with fun, interactive lessons that let you play with concepts, like their new Programming with Functions course, which enables you to visualize functions by applying them to images. Brilliant is also a great place to build your foundations, like their course on logic, which is the perfect way to develop a rock-solid intuition for the kind of rigorous thinking you need in formal math. Beyond these, Brilliant helps you become a better thinker and problem solver with thousands of visual interactive lessons in math, science, programming, and AI. To get started, you can go to brilliant.org/ankyog. Click the link in the description or scan the QR code on your screen to get a full 20% off their annual premium subscription. A huge thank you to Brilliant for sponsoring this video. Let's explore more proofs. Theorem EV10 is the proof that 10 is even. What's the definition of even? Just unfold even to see it. The unfold tactic unfolds definitions. We can see that 10 is even only if there exists a number r such that 10 equal r plus r. Clearly, r should be 5. So let's use 5 and the proof is over. Use 5 substitutes r for 5 and proves this trivial result. Notice that use 1 substitutes r as 1, but we can't prove this, it's false. What we just saw is the introduction of an exist statement. We have to use the correct value k and then prove pk for that value. Theorem 2div even is a proof of for all n, even n implies 2 divides n. Please note, the character for divides is typed as \bar, not just vertical bar. Start by assuming n with the for all introduction, intro n. The goal is now an imply statement. In normal language, we would assume n is even. In lean, intro n even. And n even is now the proof of even n. What we just did here is the implies introduction. To prove P implies Q, intro HP as the proof of P and then prove Q using that. We can unfold even at the assumption and see that n even is the proof of an exist statement. Clearly, n must equal r plus r for some r. So let's obtain a number r and a proof hr from n even. The tactic state now contains a number r and the proof that n equal r plus r. What we just did here is an exists elimination. Obtain the number and the proof for that number from an exists proof. We have almost solved this. Have n equal 2r be a proof that n equal 2 times r. Our goal changes to this sub-goal. Rewrite hr in the goal to rewrite n as r plus r and use ring to solve r plus r equals 2 times r. That finishes the sub-goal. Going back to the main goal, simply rewrite n as 2 times r using rewrite n equal to r, and our goal appears trivial. I mean, surely 2 must divide something it is very clearly a factor of. If you ever think something looks trivial, try using the simp tactic. In this case, it works. Our proof is correct. So, what really is our proof 2div even? Well, it's a function that takes in a number n and then takes in a proof of even n for that n and returns a proof of 2 divides n. Check 2div even and you'll see its type signature. If I give it 10 as input, it is now the proof of even 10 implies 2 divides 10. Do I have a proof of even 10? Yeah, EV10, which we proved before. Give that as input and look, it's now the proof of 2 divides 10. Hence, I could prove 2 divides 10 by having h be 2div even on 10 and EV10. The goal is now exactly h. I cannot change the 10 to 8 because then it expects a proof of even 8 instead of even 10. This is the implies elimination. Given an implies proof IM, give it the proof of P as input and get the proof of Q in HQ. Let's now define our own PrimeNum. Def PrimeNum given a natural number n is a proposition that is defined as n greater than or equal to 2 and for all m of type nat, m divides n implies m equal 1 or m equal n. That is, if any number m divides n, it must be 1 or n itself. Let's try to prove theorem not prime 1, a proof of not PrimeNum 1. Now, not P means the same thing as P implies false. Assume 1 is PrimeNum using the implies introduction, intro PR1. Our goal is now to show this is false. Unfold the definition of PrimeNum at PR1. Since PR1 is a proof with 2 components joined by AND, we can take it apart with obtain HL and HR from PR1. Given an AND proof, taking it apart using obtain is the AND elimination. Notice that the tactic state now has HL and HR as 2 separate proofs. Clearly, HL is false, so we will use the contradiction tactic. Contradiction to show false. And the proof is complete. Similarly, let's do theorem not prime 9 is a proof of not PrimeNum 9. Just like last time, intro PR9. Unfold the definition of PrimeNum at PR9 and obtain HL and HR from PR9. This time, HL is true, but HR is false, as 3 is a counterexample. Since HR is a for all statement, using elimination, have HR3 be HR with 3 as input. This will replace the M in HR with 3. HR3 is now an implies proof. To get the proof of 3 equal 1 or 3 equal 9 out of it, we need to give it a proof of 3 divides 9. Have div be the proof of 3 divides 9, which we can prove using norm num. Perform implies elimination on HR3 with div as input to get OR cases as the proof of 3 equal 1 or 3 equal 9. Let's split these using OR cases OR cases with C1 bar C2. Notice that we have two cases, INL with C1 as 3 equal 1's proof and INR with C2 as 3 equal 9's proof. Given an OR proof, taking it apart using OR cases is the OR elimination. Both cases have a contradiction, so the contradiction tactic solves both. To show their separate cases, we can indent them with a \dot. And finally, our last proof before the big ones. Theorem prime 5 is a proof of PrimeNum 5. We can unfold PrimeNum and see that our goal is an AND statement. If we can prove both parts, then we have proven the goal. Let's have G1 as a proof of 5 greater than or equal to 2. And have G2 as a proof of for all m of type NAT, m divides 5 implies m equal 1 or m equal 5. Our goal is now exactly the pair G1 and G2, and the goal is solved. We just need to fill in the sorries. An AND statement's proof is exactly the pair of the proofs of its two components. That's the AND introduction. We can prove 5 greater than or equal to 2 using norm num. For G2, we must first apply for all AND implies introductions with intro m and hm div 5, assuming m and the proof of m divides 5. We could solve this by going case-wise on m using the match tactic. Let's match m with 0, 1, 2, 3, 4, 5 and n plus 6, where n plus 6 basically means 6 and above. For 0, the assumption that it divides 5 is false, so contradiction solves it. The same applies to 2, contradiction, 3, contradiction, and 4, contradiction. For 1, the left part 1 equal 1 is true, while the right one 1 equal 5 is not. Let's have h be a proof of 1 equal 1 by norm num. The goal is exactly OR.INL_H. Proving an OR statement requires you to prove only one side. We just did the introduction for the left side. Similarly, in 5, the right part is true, while the left one is not. Let have h be a proof of 5 equal 5 by norm num. The goal is now exactly OR.INR_H. That's the OR introduction for the right side. I can't write OR.INL_H here because then it expects a proof of the left side, 5 equal 1. Finally, for n plus 6, we can use a theorem from Mathlib, nat.equals0 of divides of less than. I know, quite a mouthful, but just look at its type signature. If you give it a proof of a divides b and b less than a, it will give you a proof of b equals 0, which is obvious. If a divides a number less than it, that can only be 0. Have h1 be a proof of 5 less than n plus 6, which can be solved by norm num. Now have h2 be the theorem that we just saw, with hm div 5 and h1 as inputs. Over here, a and b match up with 5 and n plus 6, so we should get 5 equals 0 out. And clearly, h2 is now a proof of 5 equals 0, hence contradiction. And we've solved every case. The proof is complete. We are finally ready to tackle the big 3 problems. These proofs are going to be slightly long and involved. I will be going through a lot of details fast, so please pause whenever you need to. I'd recommend you open up Lean, take a careful look at the Mathlib theorems we'll use, and along with the tactics, keep the introduction and elimination rules in mind. Let's start. The first proof is really interesting. We will show that there exists real x and y, where irrational x and irrational y, along with not irrational x to the power y. Using the law of the excluded middle, square root 2 to the power square root 2 is either rational or irrational. If it is rational, then let x and y both be square root 2. X to the power y is rational according to our assumption, and we're done. If it is irrational, then let x be square root 2 to the power square root 2, which is irrational according to our assumption, and let y be square root 2. X to the power y is now root 2 to the power root 2 whole to the power root 2, which equals root 2 square, which equals 2, which is rational, and we're done. We still don't know which of these is correct. It all depends on whether root 2 to the power root 2 is rational or irrational. But it doesn't matter, we've proven our theorem for both cases. Let's check out the theorem classical.m. For any proposition P, it returns a proof that P or not P is true. Let's perform for all elimination on this with the proposition irrational square root 2 to the power square root 2. This gets us M as the proof of an OR statement. Use OR elimination on this to get two cases, HL and HR. The first case, HL, assumes that square root 2 to the power square root 2 is irrational, while the second case, HR, assumes it is rational. In both cases, the goal is an exist statement which demands the values of x and y. For the first case, x must be root 2 to the power root 2 and y must be square root 2. So let's use those two values. Have irrat be the proof that irrational square root 2 and have rat be the proof that rational root 2 to the power root 2 whole to the power root 2. By AND introduction, the goal is now exactly the three assumptions put together. Similarly, for HR, we need x and y both to be square root 2. So, use square root 2 and square root 2. Again, have irrat be the proof that irrational square root 2. The goal is now exactly the proof irrat twice and HR put together. And we're done. All we have to do is fill in the sorries. There's a Mathlib theorem, irrational square root 2, which states square root 2 is irrational. Hence, we can replace this sorry with exact irrational square root 2, and this one too. If we had a proof EQ that square root 2 to the power square root 2 whole to the power square root 2 equal 2, then we could prove not irrational the same value by simply rewriting EQ into this. Proving not irrational 2 looks trivial, so I'll just simp and it's solved. To show that this equation holds, we will use the calc tactic, which allows for a cleaner way to prove equations like this. First, root 2 to the power root 2 whole to the power root 2 equals root 2 whole to the power root 2 times root 2. Then that equals root 2 square, which then equals 2. The last two can be solved using simp. The first one will require us to use a Mathlib theorem, real.rpower_mul. If given a proof of 0 less than or equal to x and two more numbers y and z, it will give me a proof of x to the power y times z equals x to the power y whole to the power z. We'll have to show that 0 is less than or equal to square root 2, which simp can handle. Then we'll have h be this theorem with non-neg square root 2 as the proof of 0 less than or equal to x and square root 2 and square root 2 as y and z. If we rewrite this into the goal, both sides are equal and we're done. The entire proof is complete and correct. The next proof is on the existence of infinite primes. This can be written as for all n of type nat, there exists P of type nat such that nat.prime p and p greater than n. Essentially, no matter how big a natural number you pick, there will always be a prime number greater than it. We can assume any arbitrary n and consider the number n factorial plus 1. It must have some prime factor p, that is, p is prime and divides it. Let's assume that p is less than or equal to n. From this, p must divide n factorial. But since p divides n factorial plus 1 too, it implies p divides 1. Since p is prime, it must be greater than 1. But now, p divides a number that is less than itself. Such a number can only be 0, which is false. Taking this fact, it implies by contradiction that p greater than n. Thus, for any n, we have a p which is prime and greater than n, which proves that there exist infinite primes. The lean proof is going to be a little intense. The goal is a for all statement, so use the for all introduction rule and intro n. To show that n factorial plus 1 has a prime factor, we will use this Mathlib theorem, nat.exists prime and divides. But this needs a proof that the number can't equal 1, as 1 has no prime factor. So first, have a proof, not 1, of n factorial plus 1 not equal to 1. The theorem nat.factorial pos tells us that 0 is less than n factorial for any natural number n. Since this is a for all statement, use for all elimination with the number n. Have h be nat.factorial pos with n as input. And out we get the 0 less than n factorial proof. It's simple linear arithmetic to show from this that n factorial plus 1 cannot be 1. That's what the linarith tactic was made for. And it's solved. Since nat.exists prime and divides is an imply statement, have p exists be the proof with not 1 as input, which is the implies elimination. Since p exists is now an exist statement with an AND statement inside, use obtain to take apart the three components of p exists, performing both exists and AND elimination in one move. Look, we now have the exact three assumptions we had during our informal proof. The goal is an exists statement and p is the prime we need. So let's use p, which is the exists introduction. The goal is now just an AND statement, and we have already the proof for the left part. If only we had pgtn as a proof of p greater than n, then using an introduction, the proof would be exactly the pair of the proof that p is prime and the proof that p greater than n. And it works. Now we have to prove p greater than n by showing that p less than or equal to n leads to false. Let's assume we have a proof plen false of not p greater than n leads to false. Checking classical.by contradiction tells us that it takes in a proof of not p implies false and gives a proof of p. We can perform implies elimination by giving it the proof plen false, with the goal being exactly h. All that's left is to prove plen false. The implies introduction tells us to intro plen, which is now the proof of not p greater than n. We'll use a new tactic, push neg at plen, which converts not p greater than n to p less than or equal to n. Now, remember this sequence in our informal proof? Let's write down the basic structure of it here. Have pgt1 be the proof of 1 less than p. Have p divides nf be the proof of p divides n factorial. Have p divides 1 be the proof of p divides 1. And have f be the proof of 1 equals 0. At this point, contradiction will solve the goal using the proof of 1 equals 0. Filling the remaining stories is a bunch of grunt work using the Mathlib theorems. The theorem nat.prime.2lay gets us the proof of 2 less than or equal to p, which linarith can use to prove 1 less than p. We can also prove 0 less than p using linarith directly. The theorem nat.divides factorial with the fact that 0 less than p and p less than or equal to n proves p divides n factorial. The theorem nat.equals 0 of divides of less than with the fact that p divides 1 and 1 less than p proves 1 equals 0. The only tricky part is p divides 1. The theorem nat.divides add right tells us that if we have a proof of a divides b, then a dividing b plus c is the same as a dividing c. For any two propositions p and q, p equivalent to q is the same thing as p implies q and q implies p. Hence, we can use AND elimination to obtain the two proofs HL and HR from nat.divides add right with the proof of p divides n factorial as input. Both HL and HR are implication statements, and $m is the unknown variable c. Since we want a proof of p divides 1, we should use HL and give it the proof of p divides n factorial plus 1. Hence, the goal is exactly HL with p divides n fp1 as input. And we're done. The entire proof is complete. Our final proof uses the axiom of choice. We need to show that every onto function f from a to b has a right inverse. In other words, there exists a function g from b to a such that for all y in b, f of g of y equals y. Let's start. Since f is onto, it means that for any y in b, there exists a non-empty subset of a which maps to y under f. Define g such that g of y chooses an element from this subset using the axiom of choice. And we know that this maps back to y under f. Hence, g is the right inverse we're looking for. Let's first open classical so we can just write choose instead of classical.choose. Theorem surj implies right inverse is the proof that for any types a and b, for all f from a to b, if f is surjective, then there exists a g from b to a, such that for all y in b, f of g of y equals y. Let's introduce the function f and assume the proof surj f. F is surjective. Unfold the definition of surjective at surj f. Notice that if I give surj f any input y from b, it will give me a proof that there exists an a such that f of a equal y. The choose theorem states that if you give it an exists proof h, it will choose one of those elements. Now let g be a function that takes a y from b and chooses from surj fy. That is, it will choose an a from the proof of there exists a such that f of a equal y. We can now use g as the right inverse we need. Introduce an arbitrary b of type b. In the goal, gb must be choose surj fb based on the definition of g. So let's unfold g. Here's the thing. The element choose surj fb would have been chosen from there exists a such that f of a equal b. That means f of choose surj fb equal b must be true, which is the goal. This is exactly what the choose spec theorem states. Given an exists proof h, if you choose an element from that exists proof, then it satisfies the condition p of the exists statement. Let's have h be choose spec with the surj b proof as input. And the goal is exactly h. We're done. And that was it. If you want to see more such content on mathematics and logic, like and subscribe and hit that notification bell. I'll see you in the next video.